Let's just jump right in. When we look at modern machine learning algorithms, I think it's really easy to assume they're built on some kind of pure, undeniable cosmic logic, right? But the truth is actually kind of wild. Algorithm design is absolutely packed with seemingly arbitrary human choices. It's a real puzzle, and today we're going to crack it open.
So here is the central mystery we're looking at today. Out of all the mathematical operations in the entire universe, why is squaring the error the universal standard in so many models? Seriously, we see this everywhere in data science. But why exactly do we do it? Okay, let's visually ground this using good old linear regression. Imagine you've got a bunch of one-dimensional training examples scattered around. Our goal is super simple. We just want to draw a regression line that gets as close to all those training data points as humanly possible. That way, we can actually predict new data down the road.
But to get that line in the exact right spot, we need a perfectly objective way to calculate a penalty every single time our predicted line misses a real data point. And that is exactly what a loss function is. In plain English, it's just a measure of penalty for the misclassification or the error of a specific example.
Now things get really interesting when we look at our main suspects for calculating this penalty. I mean, the absolute most obvious choice would be the absolute value difference, right? Just measure exactly how far off the line is from the data point. Simple. But instead, the absolute gold standard across the industry is the squared error, where we take that difference and multiply it by itself.
And honestly, the plot thickens here because there are plenty of other completely logical possibilities we could use. We could easily cube the difference. We could use a binary loss, just assign a 1 if the prediction is different and a 0 if it's the same. We could even use higher degree polynomials. All of these make perfect sense, which just deepens the mystery of why the squared error always seems to win out.
Well, the answer takes us all the way back to the year 1705. French mathematician Adrien-Marie Legendre, the guy who first published the sum of squares method, literally just said that squaring the error before summing is quite simply convenient. Yep, you heard that right. This foundational choice in modern artificial intelligence was driven purely by historical mathematical convenience.
But we have to ask, what did Legendre actually mean by convenient? Well, it all comes down to continuous derivatives. See, unlike absolute values, which graph with these really sharp, jagged corners, squares give us beautiful, smooth curves. They are smooth functions with continuous derivatives.
And it turns out, the math of minimizing empirical risk essentially demands these smooth functions. If you use a function that lacks a smooth curve, like the absolute value function, it creates these incredibly frustrating, unnecessary difficulties when we try to use linear algebra to find closed-form solutions to our optimization problems.
And having a smooth curve, that unlocks the actual mathematical magic of optimization. Because we have a continuous derivative, we can easily calculate the gradient of the function. Then we simply set that gradient to 0. Why? Because the value of a gradient at the absolute bottom, the absolute minimum of a function, is always 0. This neat little trick perfectly locates the absolute minimum of our penalty, handing us the exact optimal values for our parameters, w and b. Now, beyond just the elegant algebra, there's actually a highly intuitive secondary benefit to this math. Squared penalties aggressively exaggerate the difference between the true target and the predicted one. Think about it. If an error is small, squaring it keeps the penalty pretty small. But if our prediction misses by a huge margin, squaring that larger error heavily, and I mean aggressively, punishes the model, forcing it to adjust.
At this point, you might be wondering, well, why don't just make an arbitrary choice to use a wildly complex model so we can hit every single data point perfectly? Well, notice what happens when a super complex polynomial of degree 10 is used instead of a straight line. Sure, it hits almost all our training data perfectly, but look at the edges. The predictions plunge downward completely out of nowhere. It completely and wildly fails to predict new, unseen information. This is classic overfitting.
And so, this brings us to the power of simplicity. This is exactly why we rely on simpler linear models paired with squared loss. This wonderfully convenient mathematical combination is chosen specifically because it prevents the wild overfitting we literally just saw. A simpler model rarely overfits, which means it generalizes much better out in the real world.
Okay, let's switch gears and transition to a slightly different problem, binary classification. This perfectly showcases how another type of model makes its own very deliberate, convenient mathematical choices. Take a look at the standard logistic function. You might know it as the sigmoid function. It has this incredible smooth curve that neatly spans exactly from 0 to 1.
That makes it the absolute perfect mathematical tool for interpreting outputs as probabilities.
But using this specific curve fundamentally changes our ultimate goal. Let's contrast the two for a second. In linear regression, like we talked about, our goal is to minimize the average loss, specifically shrinking that squared penalty. But in logistic regression, we shift the objective completely. Instead of minimizing a penalty, we're actually trying to maximize the likelihood of the training data according to our model.
And the math behind logistic regression is just fascinating. Because it relies on the exponential function to create that neat 0 to 1 curve, it actually becomes mathematically way more convenient to maximize the log likelihood rather than the standard likelihood. Why? Because the natural logarithm is a strictly increasing function. Maximizing it gives us the exact same solution to our optimization problem, but the math, it's vastly easier to compute.
But of course, there is a catch. Unlike our neat squared error trick from earlier, logistic regression doesn't have a simple closed-form solution. We can't just set the gradient to 0 and magically solve an algebraic equation. Instead, we have to rely on complex numerical optimization methods, things like gradient descent, to gradually, step by step, walk our way down to the best parameters.
Which leaves us with a really fascinating thought to ponder as we wrap up this explainer. If our absolute most cutting-edge algorithms are built on convenient math from 1705, driven simply by a need for smooth derivatives and easy algebra, what other seemingly arbitrary choices are shaping the AI of tomorrow? The systems governing our world aren't just pure inevitable logic. They are deeply human, shaped by the incredibly practical choices of mathematicians working centuries ago. Thanks for tagging along, and always keep questioning the math behind the machine.